Today, we're going to talk about the space between things, about the space between galaxies, the dark, almost incomprehensibly empty corridors that separate island universes from one another across a cosmos so large that the numbers required to describe it stop feeling like numbers at all and begin to feel like mythology. Somewhere out there, beyond the last star of the Milky Way, beyond the Magellanic Clouds, beyond the scattered dwarf galaxies that orbit us like dim satellites, the light simply runs out, and what begins is not darkness in any sense your mind was built to understand. It is something quieter than that, something that has no name in any human language, because no human being has ever stood inside it, and because the universe did not make it for standing in, it made for crossing, slowly, over timescales that dwarf the age of every star that has ever burned. Tonight, we are going to cross it together. We are going to begin close, and the only place any story can honestly begin, with what we know, with what we can see, with the soft, familiar glow of the night sky above us. And then, chapter by chapter, we are going to walk away from that light. We are going to move outward to the edges of our galaxy, past the boundaries of our local family worlds, and into deep, cold, almost perfectly empty space that fills the overwhelming majority of the universe we inhabit. By the time we arrive at the end of this journey, the stars above you tonight may feel different. Not smaller, exactly, but more precious, more improbable, more like what they truly are, rare islands of warmth and complexity, burning against a backdrop of silence so vast and so complete that their very existence borders on the miraculous. Let us begin. On a clear night, far from the light pollution of any city, the sky above you appears full. That is the word most people reach for. Full. The ancient Greeks believed the stars were holes in a great celestial sphere, and light from a fire beyond poured through them. The poets of every civilization looked up and felt surrounded, cradled, enclosed within something immense but not empty, something populated, something alive with distant suns. That feeling is one of the most beautiful lies the cosmos tells. The human eye, on the darkest night in the most remote location on Earth, can resolve perhaps 9,000 individual stars, 9,000 points of light scattered across the entire dome of the sky. It feels like a multitude. It feels like abundance. And in the context of human experience, of cities and streets and the narrow corridors of ordinary life, it is a multitude. It is abundance. But 9,000 is nothing. The Milky Way, the galaxy in which every single one of those 9,000 visible stars resides, contains somewhere between 200 and 400 billion stars. The uncertainty in that estimate is itself larger than the entire visible count by a factor of thousands. We do not know the total number of stars in our own galaxy to within 100 billion. That is how large the numbers have already become before we have even begun to speak of the space between galaxies. All 9,000 stars visible to your naked eye tonight are within a few thousand light years of Earth. Most are within a few hundred. On the scale of the Milky Way, which stretches roughly 100,000 light years from edge to edge, those visible stars form a tiny luminous neighborhood, a village, not even a town. You are, in the most literal astronomical sense, seeing only the block you live on. Everything else, the billions of other stars in the galactic disk, the ancient red giants in the galactic bulge, the globular clusters orbiting in the halo like frozen cities of a million suns each, all of it is invisible to you tonight, drowned in the noise of distance and lost below the threshold of unaided human vision. And this is still only our galaxy. There is a concept in astronomy called the local bubble. It is the region of relatively low-density interstellar gas within which our solar system currently travels. It stretches roughly 1,000 light years in various directions and was probably carved out by a series of supernova explosions over the past 10 to 20 million years. Explosions that swept the surrounding gas away and left us drifting in a kind of rarefied pocket. The stars you see tonight, the ones that make up the familiar constellations, Orion, the Big Dipper, Cassiopeia, are, nearly all of them, stars that share this bubble with us. They are our closest cosmic neighbors. They are the stars whose light takes years to reach us, not centuries, not millennia. They are, in galactic terms, our next-door neighbors. And yet even they're farther away than any human being has ever traveled, by a factor so large it dissolves ordinary intuition on contact. Proxima Centauri, the nearest individual star to our sun, is 4.24 light-years away. The fastest spacecraft humanity has ever built, the Parker Solar Probe, which in 2024 reached speeds of approximately 635,000 kilometers per hour, would take roughly 6,300 years to cover that distance, not accounting for deceleration, not accounting for the fact that the probe is not aimed in that direction, just the raw mathematics of our fastest machine crossing the smallest possible interstellar gap. The night sky is not full. The night sky is almost entirely empty, and the few lights we can see are so far away that reaching them would outlast every civilization that has ever existed on this planet. We look up and feel surrounded, but we are not surrounded. We are alone in the middle of an almost unimaginable vastness, and the stars we see are the small, close, forgiving exceptions that make the rule bearable. That rule, the true rule of the cosmos, is distance. Cold, silent, impassive distance. And tonight, we are only beginning to understand it. Most people, when they think about the Milky Way, imagine the band of faint light visible on summer nights in the countryside. That soft, cloudy arc that stretches from horizon to horizon, slightly brighter in some directions than others, trailing off into something that looks almost like a smear of milk across dark velvet. That band is a galactic disk. It is a flattened structure of stars, gas, and dust in which our solar system is embedded. A disk approximately 100,000 light-years in diameter, and somewhere between 1 and 2,000 light-years thick in the region where we reside, thickening toward the central bulge, thinning toward the outer edges. When you look at the galactic band, you are looking along the plane of that disk, seeing the accumulated light of billions of stars are too distant and too densely packed to resolve individually. The galaxy seen edge on from within, like looking through the walls of a vast, flat room. But a galactic disk is not all the Milky Way is, not by a significant measure. Above and below the disk, extending in all directions into three-dimensional space, is what astronomers call a galactic halo. It is a roughly spherical structure, much more diffuse than the disk, populated by older stars, many of them ancient, formed in the early universe before the galaxy had settled into its flat configuration. The stellar halo extends somewhere between 300,000 and perhaps 500,000 light-years from the galactic center, making the Milky Way substantially larger than its glowing disk would suggest. Within the halo orbit the globular clusters tight, gravitationally bound spheres of ancient stars, some containing millions of suns, formed long before the disk itself. There are roughly 150 confirmed globular clusters in the Milky Way's halo. They are relics, time capsules. Some of them contain stars that are nearly as old as the universe itself, 12 or 13 billion years old, born when the cosmos was young, and the first heavy elements were only just beginning to be forged in the first generation of massive stars. And surrounding even the stellar halo, invisible but immense, is the dark matter halo, a structure we will return to in detail later. It extends perhaps 5 to 10 times further than the stellar halo, out to radii of 1 to 2 million light-years, and contains a majority of the Milky Way's total mass. The galaxy you see in the night sky is only the luminous center of something far larger and far more diffuse that we can only infer from its gravitational influence. Now, where does this structure end? That question is harder to answer than it might seem, because the Milky Way does not end with a clean boundary. It does not have a shoreline. It fades. The stellar density decreases with distance from the center. The stars in the outer halo grow so sparse that distinguishing Milky Way stars from the intergalactic background becomes a genuine observational challenge. There are stellar streams, the remnants of smaller galaxies and globular clusters that the Milky Way has consumed over its lifetime, wrapped around the galaxy like faint, ghostly ribbons. The Sagittarius stream is one of the most prominent. The tidal debris of a dwarf galaxy being gradually shredded and absorbed, its stars stretched into a great arc that winds around the entire sky. There are also hypervelocity stars, individual stars ejected from the galactic center, most likely by gravitational interactions with the supermassive black hole at our galaxy's core, which we call Sagittarius A star. These stars travel fast enough to escape the galaxy's gravitational pull entirely. They are the emigrants of the Milky Way, cast out by the violent dynamics of the galactic center, heading out into intergalactic space, never to return. Their existence tells us something both precise and poetic. Even our galaxy, our home structure, is not perfectly contained. It leaks. So when we speak of the Milky Way's edges, we are speaking less of a wall and more of a gradient, a place where structure becomes suggestion, where galaxy becomes intergalactic, where home becomes open ocean. Beyond those last faint stars, beyond the outermost whispers of stellar light, the true void begins. Before we step into that void, let us pause for a moment to look at what we stand to leave behind. The Milky Way does not travel alone. Like most large galaxies, it exists within a larger gravitationally bound structure, a collection of galaxies that are close enough to one another and moving slowly enough relative to one another that they will not fly apart as the universe expands. They are locked in a long, slow gravitational embrace. This collection is called the local group. The local group contains approximately 80 known member galaxies, spanning a region of space roughly 10 million light-years in diameter. Most of its members are small, dwarf galaxies, irregular in shape and modest in mass, orbiting like satellites around the two dominant members. Those two dominant members are the Milky Way and the Andromeda Galaxy, known to astronomers as M31. Andromeda is our largest neighbor. It is a spiral galaxy broadly similar in structure to our own, though somewhat larger, containing perhaps 1 trillion stars compared to Milky Way's 2 to 400 billion. It sits 2.537 million light-years away on the scale of the observable universe, which extends some 46 billion light-years in every direction from Earth. Andromeda is practically next door on the scale of human experience. It is almost incomprehensibly remote. The light you see from Andromeda on a clear autumn night, the faint elliptical smudge visible to the naked eye near the constellation Perseus, left its source 2.537 million years ago. When that light began its journey, our species had not yet evolved. Homo sapiens would not appear for another 2.5 million years. The genus Homo itself was only just beginning to take shape. Our distant ancestors were Australopithecus or early Homo habilis, walking the African plains, making simple stone tools, entirely unaware that one day one of their descendants would stand under the same sky and understand what that faint smudge was. We look at Andromeda, and we see the past. We see it as it was when our ancestors were not yet human. We see it as it was before the first stone was deliberately shaped, before the first fire was controlled, before the first word was spoken or the first story was told. And that is our nearest large neighbor. The Triangulum Galaxy M33 is a smaller spiral, sitting 2.73 million light-years away. The Large and Small Magellanic Clouds, irregular dwarf galaxies that are loosely bound to Milky Way and visible to the naked eye from the southern hemisphere, are approximately 160,000 and 200,000 light-years distant, respectively, making them the closest external galaxies to Earth. The dwarf galaxies that orbit both the Milky Way and Andromeda are scattered throughout the local group in a gravitationally complex distribution. What holds a local group together is gravity. Specifically, the mutual gravitational attraction of all this mass, dark and luminous alike, pulling the members toward one another or at least slowing their divergence as the universe expands. The local group is, in cosmic terms, a bound system. Its members will not, barring some extraordinary external perturbation, fly apart into the void. In fact, quite the opposite is happening. Andromeda and the Milky Way are approaching each other at roughly 110 kilometers per second. The two galaxies are on a slow-motion collision course, one of the best studied predicted events in astronomy. In approximately 4.5 billion years, they will begin to merge, not a crash in any explosive sense. Galaxies are so diffuse relative to distances between their stars that a merger is less a collision and more an interpenetration, a long, complicated gravitational dance that will take billions of years to resolve. The result, models suggest, will be a large elliptical galaxy, tentatively and somewhat poetically called Milkomeda or Milkdromeda by some astronomers. Our sun will almost certainly survive this event, though it will likely end up in a very different part of the resulting merged structure. But all of this, all of the local group's rich complexity, its spirals and dwarfs and streams and impending mergers, occupies only a tiny fraction of the observable universe. 10 million light-years, set against 93 billion light-years of observable space, is a small thing. It is the neighborhood, the city block, the village. Beyond it lies something else entirely. Beyond the local group, the filaments of the cosmic web stretch away into distances that make even Andromeda feel intimate and close. And between those filaments, between the places where gravity has drawn matter together into luminous structures, lies the void, the deep, cold, almost perfectly empty void. We are about to enter it, step outside the local group, not literally. No human technology could accomplish this in any time frame a human civilization could survive, but conceptually, in the way that science allows us to travel without moving, step outside the local group and look around. What do you find? The first thing you notice is that the nearest galaxy cluster, a gravitationally bound collection of hundreds or thousands of galaxies, far richer than our small local group, is the Virgo cluster, sitting approximately 53 million light-years from Earth. It contains more than 1,000 confirmed member galaxies, and is the dominant mass concentration in our cosmic region. The Milky Way, Andromeda, and the entire local group are loosely associated with a much larger structure centered on the Virgo cluster, a supercluster we call Laniakea, which we will discuss in detail shortly. But between us and the Virgo cluster, there is not a great deal of matter. There is some scattered galaxies, diffuse gas, the faint whisper of the cosmic web's filaments. But mostly there is space. The second thing you notice as you move further out, past the Virgo cluster, past the other galaxy groups and clusters scattered through our region of space, is that the universe begins to reveal its true texture. Not the texture of stars or even galaxies, but the texture of the large-scale structure itself. A vast, three-dimensional web of filaments and sheets, nodes and voids. And those voids, the spaces between the filaments, are not incidental. They are not gaps in the furniture. They are the dominant feature. When astronomers map the distribution of galaxies across the universe, and they've been doing this systematically for decades, through surveys like the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and more recently the DESI Survey, which began releasing groundbreaking results in 2024. What they find is that galaxies are not scattered evenly. They cluster into filaments and sheets, separated by enormous regions of relative emptiness. The voids can span hundreds of millions of light-years. The average density of matter inside them is dramatically lower than the cosmic average, which is itself extraordinarily low. Here is the number that puts that in perspective. The average density of matter in the universe, averaged across everything, all the galaxy clusters, all the filaments, all the voids, all the dark matter, and all the visible gas, and all the stars, and all the planets, and all the dust, is approximately 5 to 6 hydrogen atoms per cubic meter. 5 or 6 atoms per cubic meter. That is the cosmic average. That is the universe's general density of ordinary matter. In the voids between filaments, the actual density of observable matter drops to a small fraction of even that extraordinarily low average. We are talking about conditions so empty that they make the best laboratory vacuums ever created on Earth look positively crowded by comparison. The best vacuum achievable in a terrestrial laboratory contains on the order of 100 to 1,000 particles per cubic meter. The intergalactic voids contain perhaps a single particle per several cubic meters, or even less, depending on location. There is a technical name for material that fills this space. It is called the intergalactic medium, abbreviated as the IgM. Despite its name, the intergalactic medium is not a medium in any sense that word carries in everyday life. It is not a substrate. It is not a fluid in any practically meaningful sense. It is an extraordinarily diffuse plasma, ionized gas, mostly hydrogen and helium left over from the Big Bang, so tenuous and so spread out that it is almost indistinguishable from nothing. Almost. The IGM is not completely uniform. It has structure, texture, not the dramatic structure of galaxies and filaments, but a subtler architecture, tracing the cosmic web in faint, gossamer threads. It is heated by the radiation of quasars and young galaxies. It undergoes its own slow, diffuse dynamics. Astronomers study it through a technique called the Lyman alpha forest, analyzing the way distant quasar light is absorbed as it passes through sheets and filaments of intergalactic gas, each absorbing cloud leaving a distinct fingerprint in the quasar spectrum. The pattern of these absorptions, dense as tree rings, tells us about the structure and temperature and chemical composition of the IGM at different epochs in cosmic history. But understanding all that intellectually does not quite communicate what would feel like, if feeling were possible, to be inside the void. Imagine you are not inside a galaxy. Imagine you are in the deep intergalactic medium, billions of light years from the nearest large galaxy cluster, somewhere in the interior of a supervoid. Around you in every direction, nothing. No stars, no dust, no planets, no magnetic fields worth mentioning, no cosmic rays of appreciable energy. The nearest source of concentrated light is hundreds of millions of light years away in every direction, a faint smudge, unresolvable without instruments, barely distinguishable from the cosmic microwave background radiation that fills all of space at a temperature of approximately 2.7 Kelvin. The temperature of that radiation, 2.7 degrees above absolute zero, is also approximately the temperature of the void. It is the coldest cold that nature, left to its own devices, naturally produces, colder than interstellar space inside galaxies, where starlight and cosmic rays provide additional energy, colder than nearly anything a laboratory could produce without deliberate effort, and utterly, perfectly quiet. This is what the universe mostly is. Not stars, not galaxies, not the luminous, dynamic structures we focus on in almost every documentary ever made about the cosmos. The universe is mostly and fundamentally this dark, cold, near-empty space, interrupted only rarely by the fragile, temporary miracle of matter clustering together into something as complex as a star. We need to talk about light, not because it is fast, though it is the fastest thing that exists, not because it is beautiful, though it is a medium through which all astronomy is done, the carrier of almost every piece of information we have ever gathered about the cosmos. We need to talk about light because it is the unit in which cosmic loneliness is measured. It is a yardstick of the void. The speed of light in a vacuum is 299,792 kilometers per second. It is a number that feels large when you state it in those terms. Close to 300,000 kilometers per second, nearly 1 billion kilometers per hour. At that speed, light crosses the diameter of the Earth in approximately 42 milliseconds. It travels from the surface of the moon to your eye in about 1.3 seconds. It crosses the average distance from the Earth to the Sun in 8 minutes and 20 seconds. These timescales feel manageable. They feel like the universe is, at the scale of the solar system, connected. 8 minutes is not very long. If the Sun ceased to exist right now, if it simply vanished, which physics does not allow but imagination can entertain, you would not know for 8 minutes and 20 seconds. You would continue to feel its warmth and see its light, entirely unaware, for that brief interval. That is how close the Sun is. But the universe does not operate at solar system scales. And as we move outward, the numbers change in a way that language was not designed to accommodate. Light takes 4.24 years to reach us from Proxima Centauri, the nearest star. We say this so often in astronomy that it begins to feel routine. It is not routine. 4.24 years is a long time. If a civilization around Proxima Centauri sent us a message today, traveling at the speed of light, the maximum possible speed, we would receive it in the year 2030. We would send a reply. They would receive it in 2034. A single exchange of messages, 8.5 years. A conversation conducted at the universe's own speed limit, taking nearly a decade per exchange. Now consider Andromeda, 2.537 million light years. A message sent today would arrive in 2,537,000 years. A reply could not reach us until 5,074,000 years from now, over 5 million years in the future. By then, if history is any guide, the humans who receive that reply will be as different from us as we are from Homo habilis. The civilization that sent the original message will have changed beyond recognition, or ended entirely, or evolved into something we would not recognize as its descendant. And Andromeda is our nearest large neighbor. It is, in the context of cosmic distances, extraordinarily close. The observable universe extends 46 billion light years in every direction. The light arriving at your eye tonight from the most distant visible galaxies left its source when the universe was only a few 100 million years old, when it was less than 3% of its current age. Those galaxies, by now, are no longer where the light says they are. They have moved. The universe has expanded. The light that left them 13 billion years ago has been traveling through expanding space, stretching as it went, arriving at your telescope or your eye redshifted, cooled, spread thin across a journey that has no human analogy. We call this look-back time. When we observe a galaxy 10 billion light years away, we are seeing it not as it is, but as it was 10 billion years ago. We are archaeologists of space. Everything we know about the distant universe is knowledge about the past, and the more distant the object, the deeper into the past we are looking. The most distant galaxies we have detected, some of which were first revealed in extraordinary detail by the James Webb Space Telescope beginning in 2022, are being observed as they existed fewer than 400 million years after the Big Bang. We are seeing infant galaxies. We are looking at the childhood of the cosmos. But there is something even more remarkable buried in this physics. Something that the speed of light, used as a unit of cosmic distance, reveals about the nature of the universe we inhabit. There is a boundary beyond which we cannot see, not because our telescopes are not powerful enough, not because the light is too faint, but because the light from beyond that boundary has not had time to reach us. The universe has a finite age, 13.8 billion years, and light can only travel at a finite speed. There exists, therefore, a sphere centered on every observer in the universe, beyond which no information can have arrived yet. This is called the particle horizon, or sometimes the cosmic horizon, and it defines the observable universe. Everything outside that boundary may be perfectly real. Almost every cosmologist believes the universe extends far beyond what we can observe, possibly infinitely far, in the models of inflationary cosmology that are currently most consistent with the data. But we cannot see it. We cannot detect it. We cannot communicate with it. It is, for all practical purposes, a different universe, one that is causally disconnected from ours, unable to influence us or be influenced by us, hidden behind a wall made not of matter, but of time. And yet, even within our observable universe, within this 46 billion light year sphere that contains everything we can ever hope to know, the distances between structures are so vast that they render the cosmos, in practice, almost entirely isolated. The light year is not merely a unit of distance. It is a unit of separation, a unit of the time it takes for information to travel from one place to another. And in a universe where the average galaxy cluster is separated from its nearest neighbor by tens of millions of light years, and where supervoids span hundreds of millions of light years of near emptiness, those units of separation describe something that goes beyond physics. They describe loneliness, not the emotional loneliness of a human being who feels unseen or unheard, but something more fundamental, a structural loneliness built into the geometry of space and time itself. The universe is not connected. It is a collection of islands in an ocean so vast that most of the islands cannot see each other's shores. The light takes too long. The distances are too great. And in the void between those islands, there is nothing, no signal, no warmth, no record of anything that has ever happened. Just a cold, dark, patient expansion of space, carrying each island further from every other island with every passing second. We will talk more about that expansion, about where it comes from, what drives it, and what it means for the ultimate fate of everything we can see. But for now, let that image settle. Let it breathe. You are on a small planet, orbiting an ordinary star, in the outer region of a large spiral galaxy, which is itself part of a modest group of galaxies, which is itself a tiny node on a vast cosmic web, surrounded in every direction by a darkness so deep and so empty that the numbers used to describe it belong more properly to philosophy than to physics. And the light, the only message the cosmos possesses, traveling at the only speed the universe allows, takes millions of years to carry news from one island to the next. You are looking up tonight at those islands. You are seeing their light. Ancient, patient, improbable light. Light that has crossed the void and arrived here at this moment. To meet your eyes, that is not nothing. That is, in fact, everything. And we are only just beginning. Pull back further, not just beyond the local group, not just past the Virgo cluster and its attendant galaxies. Pull back until the entire observable universe begins to reveal itself as a single object, not a collection of objects, not a catalog of galaxies and clusters and voids. A single, structured, coherent object, with a shape and a texture that no one anticipated, and that took most of the 20th century to confirm. What you find at the largest scales accessible to observation is a web. Astronomers call it a cosmic web, and the name is not merely poetic. It is geometrically accurate. The distribution of matter in the universe, at scales of hundreds of millions to billions of light years, resembles a three-dimensional network of interconnected filaments, long strands of galaxies and dark matter and diffuse gas, stretching across space, intersecting at dense nodes, enclosing vast interior spaces where almost nothing exists. It looks, in the maps that modern galaxy surveys have produced, remarkably like the structure of a neural network, or the fine lattice of a spider's web covered in morning dew, each droplet a galaxy cluster, each strand a filament of matter pulled thin by gravity across cosmic distances, or the foam of soap bubbles, where the matter clings to the surfaces and edges of the bubbles and the interiors are empty. These analogies are imperfect, as all analogies are, but they point at something real, something that the universe genuinely, demonstrably is. The cosmic web was first seriously theorized in the late 1970s and early 1980s by researchers including Yakov Zeldovich and his colleagues, who used analytical calculations and early computer simulations to predict that the large-scale structure of the universe should consist of sheets and filaments surrounding voids. The observational confirmation came gradually, as galaxy surveys became large enough and deep enough to map the three-dimensional distribution of galaxies over volumes of space sufficient to reveal the structure. The CFA2 Great Wall, discovered in 1989, was one of the first large-scale structures confirmed observationally, a vast sheet of galaxies stretching hundreds of millions of light years. The Sloan Great Wall, identified in 2003, was even larger. The Hercules Corona Borealis Great Wall, identified more recently, may stretch as far as 10 billion light-years across, though its status as a single coherent structure remains a subject of ongoing astronomical discussion. The DESI survey, the Dark Energy Spectroscopic Instrument, which has been operating at the Kitt Peak National Observatory in Arizona and releasing major results beginning in 2024, is currently producing the most detailed three-dimensional map of the large-scale structure of the universe ever assembled. It is measuring positions in redshifts of tens of millions of galaxies across billions of light years, tracing the cosmic web with a precision and completeness that previous surveys could not match. The maps it is producing confirm and refine the picture. A universe whose large-scale structure is dominated by a hierarchy of filaments, sheets, nodes, and voids, all of it emerging from the same initial conditions that govern the earliest moments of cosmic history. That emergence is the part of the story that deserves a moment of stillness. The cosmic web is not an accident. It is not a random scattering of matter that happened to clump in interesting ways. It is a direct, mathematically predictable consequence of two things: the tiny quantum fluctuations in the density of the very early universe, and a relentless operation of gravity over 13.8 billion years. In the first fraction of a second after the Big Bang, during the epoch of cosmic inflation, the universe underwent a period of extraordinarily rapid expansion. During this expansion, quantum fluctuations of fundamental, unavoidable uncertainty built into nature at the smallest scales were stretched to cosmic sizes. Regions of space that were infinitesimally denser than their surroundings became regions that were macroscopically, if very slightly denser. The inhomogeneities were tiny. The contrast between the dense regions and the sparse regions was on the order of 1 part in 100,000, visible today as the barely perceptible temperature variations in the cosmic microwave background radiation, the ancient afterglow of the Big Bang, first mapped with high precision by the COBE satellite in the 1990s and refined through WMAP, the Planck satellite, and ongoing ground-based experiments. But tiny as those initial fluctuations were, gravity is patient. Over hundreds of millions of years, then billions of years, the slightly denser regions attracted more matter. Gas flowed along the gradient of the gravitational potential, draining from the voids into the sheets, from the sheets into filaments, from the filaments into the nodes where great clusters of galaxies formed and grew. The voids grew emptier as the filaments grew richer. The structure amplified itself, becoming more pronounced with each passing epoch, driven by the implacable one-way ratchet of gravitational collapse. There's also another imprint woven into this structure, one of the most elegant pieces of observational evidence in all of cosmology. In the early universe, before the formation of atoms, matter, and radiation existed together as a hot, dense plasma. Sound waves, pressure waves propagating through this plasma, traveled outward from overdense regions at a speed determined by the balance between radiation pressure and gravitational attraction. When the universe cooled enough for atoms to form, approximately 380,000 years after the Big Bang, the plasma became transparent. The radiation decoupled from the matter, and those sound waves froze. They left a characteristic scale imprinted in the distribution of matter, a preferred separation distance between galaxy clusters, corresponding to the distance those sound waves had traveled before freezing. This preferred scale, known as the Baryon Acoustic Oscillation Scale, is approximately 490 million light-years. It appears as a subtle statistical excess in the correlation between galaxy positions at that separation, a ringing in the structure of the universe, a frozen ripple from the early cosmos, still detectable in the three-dimensional map of galaxies today. It serves as a standard ruler, a known physical scale that can be measured across cosmic distances and used to calibrate the geometry of the universe. It is one of the primary tools of modern cosmology and one of the primary targets of the DESI survey. The cosmic web is a record, a physical record, written in the positions of hundreds of billions of galaxies, of everything that happened in the first moments of the universe's existence. Every filament, every node, every void is a consequence, the long, slow, inevitable consequence of quantum mechanics operating in the first microsecond of time. We live in one small node of that web. Our local group is a modest cluster on a minor filament of the Laniakea supercluster, a structure approximately 520 million light-years across, containing the mass of roughly 10 million billion suns, and including the Milky Way, Andromeda, the Virgo cluster, and hundreds of other galaxy groups and clusters in a loose gravitational basin. Laniakea was identified and named in 2014 by a team led by astronomer Brent Tully, using a new method of mapping the velocity flows of galaxies, not just their positions, but the direction in which they are moving, tracing the gravitational landscape of space the way a drop of water traces the topography of the ground it falls on. We are embedded in this structure. We are downstream of it, gravitationally speaking, and around us, on scales too large for any individual galaxy to see in its own sky, the web stretches in all directions, intricate, ancient, and almost entirely empty between its luminous strands. The filaments and nodes of the cosmic web get most of the attention. They are where the galaxies are. They are where the light is. They are where the action, the star formation, the mergers, the explosive deaths of massive stars takes place. They are where we live. But the voids between them are larger, much larger. In volume, the voids dominate. The filaments and sheets, for all their visual drama in the maps, occupy a thin interconnected network enclosing vast interior spaces. If you could randomly select a point in the observable universe, the probability that it falls inside a gravitationally collapsed structure, a galaxy cluster, a filament, a galaxy, is small. The probability that it falls inside a void is far, far greater. The voids are not the margins of the cosmic web. They are, by volume, the main event, and some voids are larger than others, much larger. We call the largest of them supervoids, regions of dramatically below average matter density spanning hundreds of millions of light years. These are not merely empty stretches. They are among the most extreme environments in the observable universe, defined not by what they contain, but by what they lack. Studying them tells us, paradoxically, as much about cosmology as studying the richest galaxy clusters. The most well-known supervoid is the Boötes Void, discovered in 1981 by Robert Kirshner and colleagues during an early galaxy survey. It initially caused something close to consternation among astronomers. Where they expected to find galaxies, they found almost none. The Boötes Void spans approximately 330 million light-years in diameter, a region of space so large that if our Milky Way were positioned at its center, our astronomers would have had to develop the technology to see other galaxies before they would have discovered that other galaxies existed. The nearest galaxy clusters would have been 165 million light-years away in every direction. The night sky would have revealed only the stars of our own galaxy, and at the extreme edge of detectability, the faintest hints of the web beyond. The Boötes Void is not completely empty. Approximately 60 known galaxies have been identified within it, a number that sounds like something until you consider that a region of comparable volume in a typical part of the universe would be expected to contain many thousands. Those 60 galaxies are not evenly distributed within the void. They tend to cluster toward the interior boundary, hinting at the tendrils of filamentary structure even within the underdensity. Why is the Boötes Void so empty? The answer, in general terms, is the same process that created the cosmic web overall. Gravitational dynamics operating over cosmic time, draining matter from underdense regions into surrounding filaments and clusters. But the Boötes Void is exceptionally large even by the standards of cosmological simulations. Some papers have suggested it may represent the merger of several smaller voids over time, a cosmic coalescence of emptiness. The precise origin of the most extreme voids remains an active area of research, and it touches on fundamental questions about the initial conditions of the universe, the nature of dark matter, and the detailed physics of structure formation. Then there is the KBC void, named for researchers Keenan, Barger, and Cowie, who describe it in a 2013 paper. The KBC void is a local underdensity potentially spanning approximately 2 billion light-years, making it, in its extent is confirmed, one of the largest known voids in the observable universe. Our own local group sits near the center of it. We live inside an underdensity. The KBC void gained heightened attention because it may have cosmological implications beyond simply being an empty region. One of the most significant unresolved tensions in modern cosmology is what is known as the Hubble tension, a discrepancy between two different ways of measuring how fast the universe is currently expanding. When cosmologists measure the expansion rate using the cosmic microwave background and early universe physics, they get one value. When they measure it using the local distance ladder, Cepheid variable stars, type Ia supernovae, and other nearby distance indicators, they get a somewhat higher value. The discrepancy, roughly 5 to 10% depending on the method comparison, is statistically significant enough to suggest either a systematic error in one or both measurement approaches, or something genuinely new in the physics of the cosmos. One proposed explanation is that our position inside the KBC void means the local universe is expanding slightly faster than the cosmic average, because matter in underdense regions flows outward into surrounding filaments, adding to the local expansion velocity. This would make the local measurement of the expansion rate appear higher than the global value, potentially explaining some or all of the Hubble tension without requiring new physics. Other researchers are skeptical that the KBC void is large enough or underdense enough to account for the full discrepancy. The debate is ongoing, and it is a beautiful example of how the large-scale structure of the universe is not merely a backdrop to cosmology. It is cosmology. A third supervoid warrants attention, both for its observational significance and for the controversy it has generated. The Eridanus supervoid sits approximately 3 billion light-years from Earth, in the direction of the constellation Eridanus. It spans roughly 1 billion light-years and is notable for its possible association with the CMB Cold Spot, an anomalously large, cold region in the cosmic microwave background, identified by the WMAP satellite and confirmed by Planck, that is statistically unusual relative to the Standard Model's predictions. The proposed connection is physical. As CMB photons travel through a supervoid, they should, in principle, lose a small amount of energy due to the late-time integrated Sachs-Wolf effect, the gravitational dynamics of photons traversing underdense regions in a dark energy-dominated universe. This would make the CMB appear slightly colder in the direction of the void. Whether the Eridanus supervoid is large enough and underdense enough to account for the full magnitude of the cold spot is debated. Other explanations for the cold spot have been proposed, including statistical fluctuations within the standard cosmological model and more exotic hypotheses, such as the imprint of a cosmic texture or, in more speculative discussions, a possible signature of a collision with another universe in the context of inflationary multiverse models. The last of these is an intriguing speculation, but it remains precisely that, a speculation without confirmatory evidence, mentioned here only to illustrate the range of ideas the cold spot has inspired. The honest scientific answer, as of 2026, is that the origin of the CMB cold spot has not been definitively resolved. It may be the Eridanus supervoid. It may be a statistical fluctuation. It may be something else. The data do not yet compel a single answer, and good cosmology means living with that uncertainty rather than collapsing it prematurely into a story. The supervoids of the universe at its most extreme, not in energy or temperature or density, but in absence. They are the cosmos stripped down to its quietest register. They are the places between places, and they are, volumetrically, the largest things that exist. The voids are not quite empty. We have established that. But what actually lives in them? This is not a trivial question. The few galaxies that exist within supervoids, the 60 known inhabitants of the Boötes Void, the scattered residents of other underdense regions, are not just ordinary galaxies that happen to be in an unusual location. They are different. Their environment has shaped them in ways that decades of observation are only beginning to fully characterize, and they represent a distinct population in the ecological diversity of the universe. Void galaxies, as they are collectively known, tend to share certain characteristics that distinguish them from galaxies in denser environments. They are typically bluer in color, indicating younger, hotter stellar populations and ongoing star formation. They tend to be less massive on average. They are more likely to be irregular or loosely structured rather than the grand, swept-clean ellipticals that dominate rich galaxy clusters. They have had, in most cases, fewer interactions and mergers with other galaxies, because there are few other galaxies nearby with which to interact. This last point is significant. In the dense environment of a galaxy cluster, galaxies interact frequently. They gravitationally perturb each other's gas reservoirs. They strip each other's material through ram pressure as they move through the hot intercluster medium. They merge over time into larger and larger structures. The great elliptical galaxies that sit at the centers of rich clusters are the product of many such mergers, bloated and reddened by the accumulated stellar populations of their consumed companions. The cluster environment accelerates galaxy evolution. It pushes galaxies toward the end state of their development, old, red, gas-poor, inert. Void galaxies escape this pressure. They evolve slowly in isolation, with their gas reservoirs largely intact. They continue forming stars at a leisurely pace. They retain their irregular or late-type morphologies. In a sense, they are the universe's most pristine galaxies, the least processed, the least disturbed, the closest to the original material from which galaxies assembled in the first billion years. Studying void galaxies is, in this sense, a form of archaeological excavation. They are windows into what galaxies looked like before the dense environment had its way with them, before the mergers and the stripping and the quenching that transformed the star-forming spirals of the early universe into the red, dead ellipticals of rich clusters. There is also another category of object that drifts through the intergalactic medium in the voids, one that is even more isolated and even more poignant, if astronomical objects can be said to have such a quality: intergalactic stars. These are individual stars, not members of any galaxy, that have been ejected from their host systems and now drift through the space between galaxies alone. They end up there through a variety of mechanisms. Gravitational interactions during galaxy mergers can fling stars outward at velocities high enough to escape the merged system entirely. Tidal stripping, the process by which a passing massive object tears stars from the outer regions of a smaller galaxy, can leave streams of liberated stars trailing through intergalactic space. Hypervelocity stars, given a gravitational kick by a supermassive black hole during a close encounter, can reach escape velocity from their home galaxy and enter the void as solitary travelers. The evidence for intergalactic stars is not merely theoretical. Observations of galaxy clusters, particularly the nearby Virgo cluster, have revealed a diffuse glow of intercluster light, a faint luminosity permeating the space between cluster member galaxies. This light comes from stars that no longer belong to any individual galaxy. They have been liberated by the gravitational turbulence of the cluster environment and now orbit the cluster's collective center of mass as a diffuse stellar halo. Some estimates suggest that in rich galaxy clusters, as much as 30 to 50% of all the stars may be in this intercluster component, unaffiliated with any individual galaxy, drifting in the space between them. Beyond clusters, in the true intergalactic void, individual stars are harder to detect. They are simply too faint at these distances, but they are almost certainly there. The processes that create them operate wherever galaxies interact, and galaxies interact wherever they exist. Some of those stars will have been flung with enough energy to travel not just outside their home galaxy, but out into the supervoid itself, traveling through hundreds of millions of light years of emptiness, far from any galaxy or cluster, unlikely ever to encounter another star. Imagine being a planet orbiting such a star, not in a galaxy, but between galaxies. The night sky from such a planet would be extraordinary in its starkness. Your star would provide light and heat. Perhaps your planet would have a moon, if the system survived the ejection with its planets intact, which is not guaranteed but is not impossible. But the sky beyond your moon and beyond your star would be a darkness profound beyond anything experienced on Earth. The galaxies of the cosmic web will be visible as faint smudges, hundreds, perhaps thousands of them accessible to the naked eye, since they are large objects even at intergalactic distances, whole islands of billions of stars. But there would be no nearby stars, no constellations in any meaningful sense. The individual stars of the nearest galaxy would be hopelessly beyond naked eye resolution, their collective light merged into that galaxy's glow. The sky over an intergalactic planet would be a sky of galaxies, not stars. A sky that revealed the structure of the universe more directly and more starkly than the star-filled skies of Earth. It would be, in its own way, a magnificent sky, but it would also be a sky that left no ambiguity about how alone you were. Such a world, if it exists, and the laws of physics offer no reason why it should not, would orbit its wandering star forever, in the cold quiet of the void, with no knowledge that any other star existed within 100 million light years. Everything we have described so far, the filaments, the clusters, the voids, the intergalactic stars, the slow drift of void galaxies to the cosmic web, all of it is structure that emerges from and is held together by something we cannot see, dark matter. The name is unfortunate in some ways because it implies a simple absence, dark meaning unlighted, unlit, invisible. But dark matter is not merely matter that happens not to be glowing. It is something fundamentally different from the atoms and molecules and particles that make up everything we have ever touched or seen or built or measured in a laboratory. It interacts with gravity. This we know, because its gravitational effects are thoroughly multiply confirmed. But it does not interact with light. It does not emit it, absorb it, reflect it, or scatter it. It is invisible not because it is dark in a way that an unlit room is dark, but because it is transparent to electromagnetism entirely. Light passes through it as though it were not there, and yet it is there. It must be there. The evidence is overwhelming, accumulated across many independent observations using many different techniques, none of which require any single assumption about dark matter's nature beyond its gravitational effect. The first strong lines of evidence came from galaxy rotation curves. In a galaxy like the Milky Way, if the visible matter, the stars and gas, were all that existed, then stars in the outer regions of the galactic disk should orbit the center more slowly than stars closer in, following the same mathematical relationship that governs the orbits of planets around the sun. Vera Rubin and Kent Ford, working in the late 1960s and 1970s, measured the rotation curves of numerous galaxies and found that the outer stars did not slow down. They maintained nearly constant orbital velocities far into galactic outskirts, far beyond where most of the visible mass was concentrated. The only explanation consistent with known physics was that those outer stars were orbiting within a much larger mass distribution than the visible galaxy alone. A vast halo of mass that extended well beyond the luminous disk and dominated the total gravitational potential. Subsequent evidence accumulated from gravitational lensing, the bending of light by mass, predicted by general relativity. Massive galaxy clusters deflect and distort the light of background galaxies, creating characteristic arc-shaped images. By measuring the degree of distortion, astronomers can calculate the total mass of the lensing cluster. Consistently, the mass inferred from lensing is far greater than the mass accounted for by visible stars and hot gas, by a factor approximately 5 or 6. The Bullet Cluster, a system of two galaxy clusters in the aftermath of a collision, provided one of the most striking demonstrations. The hot gas of the two clusters, which interacted and slowed during collision, was spatially offset from the mass distribution inferred from lensing, which passed through collision largely unimpeded. This behavior is precisely what dark matter, matter that does not interact electromagnetically, would produce. The cosmic microwave background provides another line of evidence, entirely independent from either rotation curves or lensing. The pattern of temperature fluctuations in the CMB encodes, in exquisite mathematical detail, the composition of the universe at the time of last scattering 380,000 years after Big Bang. The relative heights of the acoustic peaks in the CMB power spectrum are sensitive to the ratio of ordinary baryonic matter to dark matter. The data from Planck and other CMB experiments consistently indicate that the universe contains approximately 5 times as much dark matter as ordinary matter. Approximately 27% of the total energy content of the universe is dark matter, compared to roughly 5% in ordinary matter. The large-scale structure of the universe, the cosmic web itself, cannot be explained without dark matter. Simulations of structure formation that include only ordinary matter produce a universe that looks nothing like the one we observe. Including dark matter in the form of a cold, collisionless fluid, produces simulations that match the observed cosmic web with remarkable fidelity. The Millennium Simulation, the illustrious TNG project, the Eagle simulation, and many others have demonstrated this across different levels of resolution and physical modeling. Without dark matter's gravitational scaffolding, the filaments would not have formed. The galaxy clusters would not have assembled. The voids would not have cleared to their observed depths. The universe as we know it would not exist. What is dark matter? Here we must be precise and honest. We do not know. We know what it is not. It is not ordinary matter that happens not to be glowing, brown dwarfs, cold gas clouds, dark stellar remnants, in the quantities needed to account for its effects. Searches for such objects, called MACHO's massive astrophysical compact halo objects, using gravitational microlensing, have constrained their abundance well below the required level. It is almost certainly not antimatter. If large concentrations of antimatter exist in the universe, we would observe the characteristic gamma ray emission produced when matter and antimatter annihilate at their boundaries. No such signal has been found. The leading candidates are new fundamental particles beyond the standard model of particle physics. Weakly interacting massive particles, or WIMPs, were for many years the most popular theoretical candidate. Hypothetical particles with masses in the range of 10 to a few hundred times the proton mass, interacting with ordinary matter through the weak nuclear force and gravity. Axions, much lighter hypothetical particles, originally proposed to solve a separate problem in particle physics related to the strong nuclear force, are another serious candidate and are the subject of active experimental searches. Sterile neutrinos, particles that are similar to known neutrinos but do not interact through the weak force at all, are yet another possibility. Direct detection experiments. Detectors buried deep underground to shield them from cosmic ray backgrounds, filled with ultrapure materials designed to register the rare collision of a dark matter particle with an ordinary atomic nucleus, have been searching for WIMPs and related particles for decades. The current generation of experiments, including LUX Zeppelin LZ in the United States and Xenon-T in Italy, have achieved sensitivities far beyond what was possible a decade ago. As of 2025 and 2026, no confirmed detection has been made. This does not prove that WIMPs do not exist. It constrains a range of masses and interaction cross-sections that remain viable, pushing the allowed parameter space into corners of the theoretical landscape that are harder to probe. But the absence of a detection at the previously most favored sensitivity range has led many researchers to broaden the search to alternative candidates, including lighter dark matter particles and axions. The dark matter problem is, as of this moment, one of the most significant open questions in physics. We are surrounded by it, embedded in it, held in place by its gravity, shaped by its influence on every scale from individual galaxies to the cosmic web itself. And we do not know what it is. We have never directly detected a single dark matter particle in a controlled experiment. We inferred existence with extraordinary confidence from its effects, the way you might infer the existence of an unseen river from the behavior of everything around it. The bent reeds, the wet ground, the tracks of animals coming to drink, without ever seeing the water itself. The cosmic web, with all its filaments and voids and nodes, is the track of that unseen river. The visible matter, the stars and gas and galaxies, is the wet ground. The river itself is dark matter, flowing where gravity takes it, shaping everything, seen by none of the eyes that owe their existence to what it has built. If dark matter is the skeleton of the cosmos, the invisible architecture that built the web and held it together, then dark energy is the force that is slowly, inexorably pulling it apart. Or more precisely, not pulling it apart, but ensuring that everything which is already separated will grow more and more distant with every passing year, every passing century, every passing billion years. Dark energy does not break the bonds that gravity has already forged. The local group will remain bound. The Virgo cluster will remain bound. The filaments will hold their internal structure together. But everything that is not already gravitationally linked to something else is being carried away by the expansion of space itself. And that expansion is accelerating. This was not always thought to be the case. Through most of the 20th century, cosmologists expected that the expansion of the universe set in motion by the Big Bang should be slowing down gravity, operating on all the matter and energy in the cosmos, should decelerate the expansion, perhaps enough eventually to reverse it in a final big crunch. The question was not whether the expansion was decelerating, but by how much. In 1998, two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, were measuring the distances to Type Ia supernovae in distant galaxies to determine the deceleration rate. What they found instead was that the supernovae were dimmer than expected, meaning they were farther away than expected, meaning the universe had expanded more than the standard models predicted, not less. More, the expansion was not decelerating. It was accelerating. The discovery, which earned Perlmutter, Schmidt, and Reese the Nobel Prize in Physics in 2011, required an explanation. And the explanation that best fits the data is that the universe contains a component of energy, not matter, not radiation, but something associated with space itself that generates a repulsive gravitational effect, counteracting and ultimately overwhelming the attractive gravity of matter on the largest scales. This component is called dark energy, and it constitutes approximately 68% of the total energy content of the universe. Ordinary matter is 5%. Dark matter is 27%. Everything we have ever seen, touched, or detected directly is 5% of what exists. The remaining 95% is dark, matter that does not interact with light, and energy that is associated with the vacuum of space itself. The simplest description of dark energy is a cosmological constant, represented by the Greek letter lambda. Lambda, a constant energy density of empty space that Einstein originally introduced into his equations of general relativity for entirely different reasons, then famously abandoned, and which modern cosmology has reinstated on the basis of the supernova evidence and many subsequent confirmations. The cosmological constant describes a vacuum energy that is the same everywhere in space and constant in time, a smooth, uniform background energy that fills all of space equally and drives the acceleration of expansion. Whether dark energy truly is a cosmological constant, or whether it varies in space and time, whether it is a dynamic field called quintessence or something else entirely, is one of the central questions of modern cosmology. The DESI survey, whose 2024 results attracted significant attention in the cosmological community, released early indications that the behavior of dark energy may not be entirely consistent with a simple cosmological constant, suggesting it may vary over time. These results were preliminary, and the scientific community appropriately received them with interest, but also with caution. A single data release, however large and well-crafted, is not the same as an established result. As of 2026, the nature of dark energy remains genuinely open. It may be a constant. It may be dynamic. It may be something our current theoretical frameworks do not yet describe. What we can say with confidence is its effect. The accelerated expansion means that the universe has a cosmic event horizon, a distance beyond which objects are receding from us faster than the speed of light due to the expansion of space, and from which no light or information can ever reach us. This is not a violation of relativity. Nothing is moving through space faster than light. It is space itself expanding, but the effect is real. There is a boundary, currently at a distance of approximately 16 billion light years, beyond which we are permanently cut off from any causal influence. Galaxies currently inside that horizon that are not gravitationally bound to us will eventually cross it, not by moving away, but by the expansion of space carrying them past a boundary from which light can no longer catch up to us. On a very long time scale, hundreds of billions of years, the galaxies that are currently visible to us and not gravitationally bound to the local group will recede beyond this horizon. The night sky will gradually empty. The number of galaxies accessible to observation will decrease, not because they have ceased to exist, but because space will have expanded enough that their light can no longer bridge the distance. In the far future, trillions of years hence, the local group, by then merge into a single large elliptical galaxy, may be the only gravitationally bound structure within the observable horizon. All the rest of the cosmic web, all the filaments and clusters and voids, all the billions of other galaxies visible to us today, will have receded beyond detectability. An astronomer in that far future, if any form of mind capable of doing astronomy exists, would look out from the merged remnant of the local group and see, in every direction, emptiness. Not the structured emptiness of the cosmic web we can map today, but a true and complete emptiness. The horizon of the observable universe containing only their own home structure. They would, from the evidence available to them, have no way of knowing that the cosmic web ever existed, that billions of other galaxies had once been visible from this location, that the universe had once been rich with structure on every scale. They would be epistemically isolated in a way that we, fortunately, are not. We live in a privileged moment. A moment when the universe is old enough for a structure to have formed and for beings capable of observing that structure to have evolved, but young enough for the cosmic web to still be accessible, for the billion galaxy view to still be possible, for the history of the universe to still be legible in the light that arrives at our telescopes every night. That window will not remain open forever. And the void, the expanding, accelerating, cold and dark void between galaxies and clusters and filaments, is what is closing it, slowly, patiently, with a geological calm that makes even the longest human timescales look frantic by comparison. Dark energy is the loneliness of the universe, made physical, not metaphorically, literally. It is the force that ensures that what is apart will become more apart, that the islands in the dark will recede from one another, until each island is its own entire observable universe, unable to see or reach or know any of the others. We are here before that happens. We can still see the web. We can still trace the filaments. We can still measure the voids and study the isolated galaxies that drift within them, and count the intergalactic stars, and map the invisible skeleton of dark matter that holds it all together. We are, in the deepest possible sense, early. There is a question that sits quietly beneath everything we've discussed so far, beneath the supervoids and the cosmic web, beneath the dark matter halos and the accelerating expansion, beneath every number and every distance and every timescale we have named. It is a question so fundamental that it is easy to overlook, because the answers have become so embedded in the practice of astronomy that we sometimes forget to ask it. How do we know? How do we know that Andromeda is 2.537 million light-years away? How do we know that the Boötes Void spans 330 million light-years? How do we know that the observable universe extends 46 billion light-years in every direction? We cannot travel to these places. We cannot lay a measuring tape across the cosmos. We cannot triangulate from 3 known points the way a surveyor triangulates a field. Everything we know about cosmic distances has been inferred, constructed painstakingly from behavioral light and the known physics of the objects that emit it. The story of how humanity learned to measure the universe is one of the most remarkable intellectual achievements in the history of science. It is a story built in layers, each layer resting on the one below it, each one extending our reach further into the cosmos. Astronomers call it the cosmic distance ladder, and the name captures something essential about the nature of the project. It is a ladder, not a single measurement. Each rung must be calibrated against the one below before it can support the one above. The first rung is the most direct. For nearby stars, within a few thousand light years, we can use parallax. As the Earth orbits the Sun, nearby stars appear to shift very slightly in position against the background of more distant stars. This shift is tiny. Even the nearest star, Proxima Centauri, shifts by less than 1 arcsecond, less than the apparent diameter of a coin seen from nearly 4 kilometers away. But it is measurable and it is geometrically clean. The parallax angle, combined with the known diameter of Earth's orbit around the Sun, gives the distance to the star directly, with no assumptions about the star's physical properties. The ESA's Gaia satellite, which has been conducting the most precise astrometric survey ever performed, has measured parallaxes for more than 1 billion stars, extending reliable parallax distances to several thousand light-years, and providing the most detailed three-dimensional map of the stellar neighborhood ever assembled. Gaia's data, released in a series of data, releases beginning in 2016 and continuing through the early 2020s, represent a transformation in our knowledge of the Milky Way structure. But parallax reaches its limit before we can stretch it to other galaxies. For that, we need a higher rung, and the rung that changed everything was discovered not by a famous theorist, but by a woman working as a human computer at the Harvard College Observatory in the early 20th century. Henrietta Swan Leavitt was employed to measure and catalog the brightnesses of stars in photographic plates of the Magellanic Clouds. In 1908, and with greater clarity in a paper published in 1912, she reported something extraordinary. A class of variable stars called Cepheids, stars that pulsate in brightness with a regular period, showed a clear relationship between their pulsation period and their intrinsic luminosity. The longer the period, the more luminous the star. This relationship, now called Leavitt's Law, transformed Cepheids into cosmic beacons of extraordinary precision. Measure the period of a Cepheid's pulsation, a purely observational quantity, requiring no knowledge of its distance, and you know its true luminosity. Compare that true luminosity to its apparent brightness as seen from Earth, and the distance follows directly from the inverse square law of light. Leavitt's discovery was the key that unlocked the extragalactic universe. Edwin Hubble used Cepheid variables in Andromeda in the early 1920s to demonstrate conclusively that the nebulae were not gas clouds within the Milky Way, but entire independent galaxies, vastly more distant than anyone had seriously proposed. The great debate of 1920 between Harlow Shapley, who believed the nebulae were part of our own galaxy, and Heber Curtis, who believed they were independent island universes, was settled not by argument but by measurement, by Leavitt's tool wielded by Hubble's observations. Cepheids take us to distances of tens of millions of light years, far enough to reach the Virgo cluster, far enough to calibrate the next rung of the ladder. That next rung is a Type Ia supernova. A Type Ia supernova occurs when a white dwarf star, the dense, Earth-sized remnant of a sun-like star at the end of its life, accumulates enough mass from a companion star to trigger runaway nuclear fusion. The explosion is extraordinarily luminous, briefly outshining the entire galaxy in which it resides, and, crucially, it reaches a remarkably consistent peak brightness. Not perfectly consistent. There are corrections to apply, and the details of progenitor systems are still an active area of research, but calibrated against Cepheids and nearby host galaxies, Type Ia supernovae become standard candles visible to distances of billions of light years, candles bright enough to be seen across a significant fraction of the observable universe. It was Type Ia supernovae that revealed the accelerating expansion of the universe in 1998. The standard candle that Leavitt's work ultimately made possible, through the chain of parallax to Cepheids to supernovae, led directly to the discovery of dark energy. The distance ladder, built rung by rung over a century of careful observation, reached all the way to the edge of the observable cosmos and told us something we did not expect to find. There is also a tool that does not depend on the distance ladder at all, a cosmic ruler rather than a cosmic candle, encoded in the structure of the universe itself. The baryon acoustic oscillation scale, that preferred separation of approximately 490 million light-years frozen into the distribution of galaxies by the sound waves of the early universe, provides an independent distance measurement. By measuring the statistical clustering of galaxies at different redshifts and identifying the BAO peak, cosmologists can determine distances across cosmic scales without relying on any astronomical calibration. This is one of the primary missions of the DESI survey, and its results are expected to provide the most precise BAO measurements ever obtained, sharpening our knowledge of the universe's geometry and expansion history. All of these methods, parallax, Cepheids, supernovae, BAO, rest on each other. Each is uncertain at some level. Each carries systematic errors that calibration can reduce, but never eliminate entirely. The Hubble tension we discussed earlier is, at least partly, a tension between different rungs of this ladder and different approaches to measuring the same quantity. It may reflect a systematic error somewhere in the chain. It may reflect new physics. The scientific community is actively working to determine which, with new missions, new surveys, and new theoretical frameworks. But what is remarkable, what deserves to be said clearly and without qualification, is that this ladder works. The numbers it produces are consistent across many independent methods, to within a few percent. We know the distance to Andromeda to better than 1% precision. We know the scale of the observable universe to better than 1%. We know the age of the cosmos to within tens of millions of years. We know these things not because someone told us, not because we traveled there and measured, but because generations of careful observers, working at the limit of available technology, build a ladder of inference that reaches across 46 billion light-years of space and 13.8 billion years of time. That is a human achievement of the first order, and it is one that deserves, in the quiet of this moment, a kind of reverence. We have arrived in our journey at the edge. not the edge of the universe. We have no reason to believe the universe has an edge, and considerable theoretical reason to believe it does not. But the edge of the observable universe, the boundary of the region from which light has had time to reach us in 13.8 billion years of cosmic history, the particle horizon, the cosmic horizon, the wall made not of matter, but of time. It sits approximately 46 billion light years away in every direction, not 13.8 billion light years, as you might expect if you naively multiplied the speed of light by the age of the universe. Because space has been expanding all the while that light has been traveling. The light we are receiving today from the most distant observable sources was emitted when the universe was only a few 100 million years old, from regions of space that were then much closer to us. In the time that light has been traveling, the expansion of space has carried those source regions to their current distance of 46 billion light years. We are seeing them as they were, in a location that no longer corresponds to where they are. The James Webb Space Telescope, since beginning science operations in 2022, has been pushing observational astronomy to the very edge of this horizon. It has detected galaxies forming fewer than 400 million years after the Big Bang. Early, compact, surprisingly bright objects whose properties have in some cases required adjustments to our models of early galaxy formation. The JWST has not broken cosmology, as some breathless science headlines suggested when its first results appeared, but has refined it, sharpened it, revealed new details about the earliest epoch of star and galaxy formation that will take years to fully incorporate into theoretical models. Beyond the particle horizon, we cannot see, we cannot detect, we cannot, in principle, ever receive information from those regions because the light from them has not had time to reach us, and because of the accelerating expansion, never will. Whatever lies beyond the horizon is, in the language of physics, causally disconnected from us. It cannot affect us. We cannot affect it. What is out there, almost every cosmologist working today would answer, more of the same, more galaxies, more filaments, more voids, more cosmic web. The inflationary models that best describe the early universe predict that the total extent of space is vastly larger than the observable bubble, possibly by many orders of magnitude, possibly infinitely so. In the simplest inflationary models, the universe continues far beyond our horizon in all directions, homogeneous and isotropic on the largest scales, following the same physical laws, filled with the same kinds of structures. The observable universe is a tiny, arbitrarily chosen bubble within a much larger whole. Some extensions of inflationary theory predict not just a larger universe, but a multiverse, a collection of causally disconnected regions, each potentially with different physical constants, different particle physics, different cosmological parameters. The eternal inflation scenario, developed by Andre Linde and others, suggests that inflation never truly stopped, that new inflationary bubbles continue to form perpetually, each one potentially a universe unto itself, each one expanding into a new domain of space with properties determined by random quantum processes. In this picture, our observable universe is one bubble among an infinite number of others, some of which may be very different from ours. These ideas are genuinely fascinating, and they are taken seriously by many physicists. But they are also, as of this moment, untestable. We cannot observe other bubble universes. We cannot detect them through any currently known physical channel. They make no predictions that differ from those of standard cosmology for anything within our observable horizon. They are philosophically and mathematically motivated, and they may be correct, but they are not, in the strictest sense, scientific claims that can presently be confirmed or refuted. They exist at the boundary between physics and metaphysics, and honest science acknowledges that boundary rather than pretending it does not exist. What the horizon does, in a deeper sense, is something remarkable and strange. It imposes a fundamental limit on knowledge, not a practical limit, not a limit that better technology can overcome, but a limit written into the fabric of space-time itself. There are things that are real. If the inflationary models are correct, there are galaxies beyond our horizon, real and fully physical, perhaps harboring stars and planets, and possibly even minds. that we can never know about. Their existence is real, but permanently inaccessible. They are separated from us not by distance in any human sense, but by the geometry of an expanding space-time that ensures their light will never arrive. This is a strange thing to sit with. We live in a universe that may be vastly larger than what we can see, populated by structures and possibly by minds that are as real as we are, and as permanently beyond our reach as if they did not exist at all. The horizon is not a wall. It is a shadow. The shadow cast by the finite speed of light in an expanding universe, reaching exactly as far as the age of the cosmos allows and no further. Beyond it, the unknown, and perhaps, in some philosophical sense, the unknowable. Let us try a thought experiment. Imagine a galaxy, a spiral galaxy, not unlike the Milky Way. Perhaps 200 billion stars arranged in a beautiful, flattened disk with arms trailing out from a central bar, a supermassive black hole at its core, a population of globular clusters orbiting in its halo. In most respects, it is an ordinary galaxy. It formed, as most galaxies do, along a filament of the cosmic web, assembled over billions of years from the gravitational collapse of dark matter and the gas that followed it. But this galaxy is not on a filament. It is not in a cluster. It is not even in a modest group like our local group. It is inside a supervoid. Perhaps it formed there, a rare overdensity within an underdense region, a fluctuation that managed to collapse into a galaxy despite being surrounded by a space that was, on average, emptier than the cosmic mean. Perhaps it was ejected from filament long ago by a gravitational interaction, sent drifting into the void on a trajectory that took it far from its origins. Either way, it is now deep inside a region like the Boötes Void, 330 million light-years of relative emptiness in every direction. The nearest galaxy cluster is at the edge of that void, barely visible as a faint collection of smudges at the extreme limit of detection. Suppose that in this isolated galaxy, life arises. This is not guaranteed. Life on Earth may be common or may be rare, and we do not know which, but suppose it does. And suppose that over billions of years, that life evolves intelligence. A civilization forms. It develops language, mathematics, philosophy, science. It begins to look at the sky. What does it see? It sees its own galaxy, rich and full of stars, exactly as we see the Milky Way. From inside, the galaxy looks much the same regardless of its position in the cosmic web. The disk stretches across the sky. The globular clusters orbit serenely. The central bar glows softly in the direction of the core. It is, for these observers, a complete and comprehensible universe in itself. But when they look beyond their own galaxy, when they develop telescopes powerful enough to detect external objects, they find something that would challenge every cosmological intuition. There's almost nothing there. In the direction of the nearest galaxy cluster, hundreds of millions of light years away, there are perhaps a few faint smudges. In every other direction, darkness. Not the darkness of a clouded sky, but the darkness of space containing almost no galaxies within a range that their instruments can probe. These civilizations, reasoning carefully from their observations, might conclude that the universe contained only their galaxy, not from ignorance or arrogance, but from evidence. The evidence available to them would genuinely suggest that theirs was the only luminous structure in existence. They might develop a complete and internally consistent cosmology in which the universe was one galaxy. Their galaxy, surrounded by an infinite or semi-infinite void. They would be wrong, catastrophically wrong about the structure of the universe. The cosmic web, with its billions of galaxies and vast filaments and thousands of galaxy clusters, would exist beyond their observational horizon, not because of light travel time, but simply because there is so little matter between them and the web's nearest filament that their instruments would find nothing there to detect. Their cosmology would be limited not by the speed of light, but by the accident of their location. This thought experiment is not merely a curiosity. It is a lesson in the contingency of knowledge. Everything we know about the universe is filtered through our position within it. Our location on a filament of the cosmic web, in a galaxy group, in a region of space that, while perhaps slightly underdense by the KBC void analysis, is still rich enough in nearby structure to have given us a genuine picture of the cosmos' architecture. Our cosmology is the cosmology available from where we happen to stand. A civilization in the void would have a different cosmology, not because reality is different there, but because the information available to them is different. They would be doing science as rigorously as we do ours, from observations as carefully made as ours, and they would arrive at conclusions that are genuinely, thoroughly wrong about the large-scale structure of the universe. How confident should we be, then, that our own cosmology is not similarly limited by our position? Most cosmologists would argue that we have good reasons for confidence, that the consistency of our measurements across many independent methods, the success of our models in predicting structures we had not yet observed, the remarkable agreement between CMB physics and large-scale structure surveys, all speak to a picture that is fundamentally correct even if incomplete, and that argument is compelling. But the thought experiment from a void is a useful corrective. It reminds us that knowledge has a geography, that what we can know depends on where we are, and that the universe is large enough and varied enough in its distribution of matter that different observers at different locations within it have access to genuinely different windows onto the same reality. We are fortunate in where we stand. We happen to be positioned in a cosmic neighborhood rich enough in nearby structure to have revealed the web, the voids, the filaments, to have given us, in the span of a single century of modern astronomy, a picture of the universe on the grandest scales. The civilization in the void, however intelligent and rigorous, does not have that luck. Awareness of this contingency is not a reason for despair about the limits of knowledge. It is a reason for gratitude at the particular accident that placed us where we are. Nothing crosses the void faster than light. That sentence contains within it the entire tragedy and the entire wonder of intergalactic communication. Light, electromagnetic radiation in all its forms, from gamma rays to radio waves, is the only carrier of information that the universe permits at maximum speed. And it crosses the void at 299,792 kilometers per second, without pause, without loss of direction, without degradation beyond the stretching of its wavelength that comes from the expansion of space itself. The light that arrives at your eye tonight from a distant galaxy has crossed hundreds of millions, perhaps billions of light years of nearly empty space. It has passed through the intergalactic medium, been scattered here and there by the diffuse filaments of the cosmic web, been stretched to longer wavelengths by the expansion of the universe, and finally, after a journey of incomprehensible duration, entered the small optical system of a human eye or a telescope mirror and delivered its information. Every photograph of a distant galaxy is a record of a crossing, a document of a signal that survived the void. But light is not the only thing that crosses intergalactic space. There are other messengers, more exotic and in some ways more penetrating. Gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity and first directly detected by the LIGO Observatory in September 2015, propagate across the universe at the speed of light, and they pass through matter with almost no interaction at all. The first confirmed detection, now known as GW150914, was produced by the merger of two black holes approximately 1.3 billion light-years from Earth. The distortion of space-time caused by that merger, two objects each roughly 30 times the mass of the Sun, spiraling into each other at a significant fraction of the speed of light, produced a wave that traveled outward in all directions, across 1 billion light-years of space, and arrived at Earth as a distortion of space-time so small that it moved the mirrors of the LIGO interferometers by a fraction of the diameter of a proton. The signal lasted less than a second. The journey took 1.3 billion years. Since that first detection, LIGO, Virgo, and the CAGR Observatory have detected dozens of gravitational wave events, black hole mergers, neutron star mergers, and in at least one case a merger between a black hole and a neutron star. Each event is a signal from across intergalactic space, carrying information about some of the most violent events in the cosmos. Gravitational wave astronomy is a new sense, a way of perceiving the universe that does not depend on light at all, that is sensitive to processes that produce no electromagnetic radiation, that opens a window onto the dark side of the cosmos in the most literal possible meaning of that phrase. There are also cosmic rays, high-energy particles, primarily protons, but also heavier atomic nuclei and electrons that arrive at Earth from space, carrying energies that sometimes exceed anything achievable in the largest particle accelerators humanity has ever built. The most energetic cosmic rays, called ultra-high-energy cosmic rays, carry individual particle energies equivalent to a well-thrown baseball, an extraordinary concentration of kinetic energy in a single subatomic particle. These particles travel across intergalactic space, and their origins are still not definitively established. The leading candidates are the jets of active galactic nuclei and gamma-ray bursts, the most energetic transit events in the universe. But the highest energy cosmic rays interact with the cosmic microwave background radiation as they travel, losing energy over distances of hundreds of millions of light years. This interaction, known as the GZK limit after the physicists Griezin, Zatsepin, and Kuzmin, who predicted it in 1966, means that the most energetic cosmic rays we detect must come from relatively nearby in cosmic terms, within a few hundred million light years. And then there are neutrinos, nearly massless, interacting only through the weak nuclear force and gravity. Neutrinos travel through matter and space with a ghostly indifference that makes them ideal cosmic messengers, and nearly impossible cosmic messengers simultaneously, because detecting them requires enormous instruments and still yields only a trickle of events. The most famous example of cosmic neutrinos from beyond our galaxy arrived on February 23, 1987, when a star in the Large Magellanic Cloud, approximately 168,000 light-years away, underwent a core-collapsed supernova. Before the light from the explosion reached Earth, a burst of neutrinos, roughly 10 seconds in duration, produced in the final collapse of the stellar core, arrived at 3 neutrino detectors around the world: Kamiokande 2 in Japan, IMB in the United States, and Baksan in the Soviet Union. 24 neutrinos were detected in total, 24 particles from a dying star 168,000 light-years away, detected simultaneously in 3 underground tanks on a small planet orbiting an ordinary star, providing direct confirmation of the core collapse supernova model and inaugurating the era of multi-messenger astronomy. The Ice Cube Neutrino Observatory at the South Pole has since detected neutrinos from distances far greater, including, in 2022, the first confirmed detection of neutrinos from our own galactic plane, and ongoing detections of high-energy neutrinos from extragalactic sources, with one candidate source identified as the active galaxy NGC 1068, approximately 47 million light-years distant. What has not crossed the void, and what cannot, on any timescale relevant to human civilization, is any object of human manufacture. The Voyager probes, Voyager 1 and Voyager 2, are the most distant human-made objects. Voyager 1 crossed the heliopause, the boundary of the Sun's influence, where the solar wind gives way to the interstellar medium, in 2012, and as of 2026 is approximately 24 billion kilometers from the Sun, still in communication with Earth via radio signals that take more than 22 hours to travel in each direction. It is an interstellar space, but is nowhere near leaving the solar system in any gravitational sense. The Oort cloud, the outermost region of comets gravitationally bound to the Sun, extends perhaps 2 light-years in all directions. Voyager 1 would take approximately 40,000 years to reach even that boundary. To reach the nearest star, traveling at its current speed, would take approximately 73,000 years. To cross the distance to Andromeda, 2.537 million light-years, at Voyager speed would take approximately 9 billion years. The Sun will have long since exhausted its hydrogen fuel and expanded into a red giant, consuming the inner planets. Before that journey would be complete, the void is not passable, not at human speeds, not at any speed we can currently imagine achieving. The distances are of a magnitude that dissolves even the most optimistic thinking about the technological future of spaceflight. Even a civilization that achieved 10% of the speed of light, an achievement so far beyond our current capabilities as to be essentially magical, would take 25 million years to cross to Andromeda. The void enforces its silence, not through malice but through geometry. And yet the signals come. The light arrives. The gravitational waves arrive. The cosmic rays arrive. The neutrinos arrive. The universe is not completely silent. It speaks constantly, in wavelengths of radiation and ripples in space-time and energetic particles, carrying news from across the void in the only currencies the cosmos permits. We are learning, slowly, to read all of them. In 1950, the physicist Enrico Fermi sat down to lunch at Los Alamos National Laboratory with a group of colleagues. The conversation turned, as it sometimes did in that era of expanding scientific horizons, to the question of extraterrestrial intelligence. And Fermi asked a question that has not been resolved in the 3/4 of a century since he asked it. Where is everybody? The Milky Way is approximately 100,000 light-years across. It contains 200 to 400 billion stars. It is approximately 13 billion years old. Even if intelligent life is rare, even if only one in a million star systems ever gives rise to a technological civilization, the galaxy should, in 13 billion years, have been home to thousands of civilizations. Some of those civilizations should have arisen billions of years before humanity. Even at a modest fraction of the speed of light, a civilization with a few million years of technological development could have explored or colonized an entire galaxy. The timescales allow it, even with generous margins. And yet we observe nothing. No signals, no artifacts, no megastructures, no obvious engineering on astronomical scales. No pattern in the electromagnetic spectrum that demands an intelligent explanation. The galaxy appears, from our vantage point, to be quiet, empty of minds, or at least empty of minds that are making themselves known. This is a Fermi paradox. The tension between the expectation that the galaxy should be full of intelligence and the observation that it appears not to be. There are many proposed resolutions. That life is extremely rare, that intelligence is extremely rare, that civilizations tend to destroy themselves before they can colonize a galaxy, that civilizations choose not to communicate, that they are communicating in ways we have not yet learned to recognize, that they are present but operating at scales or in modes that are invisible to our current instruments. Each of these hypotheses has its proponents, and none of them has been confirmed or ruled out. The Fermi paradox remains genuinely open, but our journey through the intergalactic void adds a dimension to this question that is sometimes overlooked in discussions of the Fermi paradox. Most treatments of the paradox operate at the level of a single galaxy, the Milky Way. They ask why the Milky Way appears quiet. They consider colonization timescales within a galaxy and whether they are consistent with a galaxy being inhabited. The question of intelligence between galaxies is almost never seriously raised, for a simple reason. The intergalactic void makes it essentially moot. Even granting the existence of civilization in Andromeda, technologically advanced, highly motivated, capable of speeds that dwarf anything we can envision, the crossing from Andromeda to the Milky Way presents barriers that no currently imaginable technology can overcome on biologically relevant timescales. At 10% of the speed of light, the crossing takes 25 million years. At 1%, 250 million years. At the speeds of our fastest spacecraft, billions of years. No biological organism can survive such a crossing. Any mission would require either self-replicating automated systems capable of crossing the void and operating coherently over geological timescales, or a civilization so different from anything biology has produced that its goals and methods are essentially unguessable. The void, in this sense, is not merely an obstacle to interstellar communication. It is a near-absolute barrier to intergalactic contact. Whatever civilizations may exist in Andromeda, and we have absolutely no evidence that any do, are effectively isolated from whatever civilizations may exist in the Milky Way. Not just isolated in the sense that communication is slow and difficult, but isolated in the sense that any physical contact is effectively impossible on any timescale shorter than a significant fraction of the age of the universe. And Andromeda is our nearest large neighbor. For galaxies separated by tens or hundreds of millions of light years, galaxies on opposite sides of a supervoid, the isolation is absolute on any biological or even technological timescale we can meaningfully contemplate. Two civilizations separated by the Boötes Void would need to exchange messages across 330 million light years, a round-trip communication taking 660 million years. Before the reply arrived, the civilizations that sent and received the messages would have had time to evolve, flourish, transform, and disappear entire many times over. The Fermi paradox, then, has two versions. The first is a galactic version. The question of why the galaxy appears quiet within itself, why we see no obvious evidence of galactic-scale intelligence. The second is the intergalactic version. The observation that even if every galaxy in the observable universe contained a thriving technological civilization, those civilizations would be as permanently separated from one another as if they existed in different universes. The void does not just delay contact, it eliminates it. Each galaxy is, on every practical timescale that matters, an island universe in the truest sense of that phrase. The physics of the void enforces a cosmic quarantine between island universes that no civilization, however advanced, is likely to break. The distances are too great, the timescales too long, the void too empty to serve as a medium for any form of meaningful exchange. This is not a depressing conclusion, though it can feel like one if approached from a certain angle. It is a clarifying one. It tells us that if we are to find evidence of other minds in the universe, we should look within our own galaxy, where the distances are merely vast rather than absolutely prohibitive. It tells us that the search for extraterrestrial intelligence is, in practice, a search within a single island, our island, the Milky Way, and that even a positive result would tell us nothing about what exists in any other galaxy separated from us by the void's impassable silence. The galaxy is our universe, in every sense that matters for a question of contact, and the space between galaxies is a final, definitive answer to the question of why the cosmos feels so quiet. It is quiet because the void made it quiet, because the same physics that built the cosmic web also ensured that its nodes were separated by distances no signal could cross in human lifetime, and no mind could cross in the lifetime of a star. We have come a long way tonight. We began with the night sky, that ancient, intimate, apparently crowded dome of light that has been looked at by every human being who has ever lived, under every kind of sky, in every kind of grief and wonder. We began with the lie it tells and the truth that lies beneath it, the truth that the sky is not full, that the stars are rare exceptions in an ocean of darkness, that the universe is, in its deepest nature, an almost perfectly empty space interrupted only occasionally and remarkably by light. We walked to the edge of the Milky Way, past the disk, past the stellar halo, past the last hypervelocity stars making their slow escape into the intergalactic medium. And we stood at the boundary where galaxy becomes void. We looked out at the local group, our small family of galaxies, and we understood how close and yet how far our nearest neighbors are. We felt, perhaps for the first time with full clarity, what a light year truly means. Not as a unit in the textbook, but as a measure of loneliness, a measure the time light must travel before news of one place can reach another. We dove into the architecture of the void itself, the cosmic web with its ancient filaments born of quantum fluctuations in the first seconds of time, the supervoids that span hundreds of millions of light years and dwarf the scale of everything we had previously considered large. We visited the few isolated galaxies that inhabit those voids, and we understood that they are different from their cluster-dwelling counterparts. Quieter, more pristine, less processed by the violent sociality of dense environments. We met the intergalactic stars, the emigrants and the exiles of the cosmic web, drifting alone to the void with no galaxy to call home. We encountered the invisible skeleton that makes all of this possible, dark matter, inferred from its effects, confirmed by many independent lines of evidence, unknown in its nature, and the expanding loneliness of dark energy, the force that guarantees the universe will grow only more and more empty, that the galaxies visible to us today will recede beyond the horizon in the far future, leaving the merged remnant of our local group in an apparent solitude that a future astronomer would have no way of knowing had once been otherwise. We learned how all this was measured. The extraordinary human achievement of the cosmic distance ladder, built rung by rung from parallax to Cepheids to supernovae to baryon acoustic oscillations, reaching across 46 billion light-years with instruments that fit in a satellite or on a mountain in Arizona. We stood at the particle horizon and contemplated what lies beyond. More universe, almost certainly, perhaps infinite universe, causally disconnected from us, real but unreachable. We imagined the civilization in the void, minds that developed science under a dark sky, and concluded, from the honest evidence available to them, that the universe contained only their single galaxy. We felt the vertigo of that thought. That knowledge has a geography, that what we can know depends on where we stand, and that we are fortunate, extraordinarily and probably fortunate, to stand where we do. We listen to the signals that cross the void, the ancient light of distant galaxies, the gravitational waves from merging black holes, the cosmic rays of uncertain origin, the ghostly neutrinos from stellar death. And we understood that the void is not completely silent, that the universe speaks across its own emptiness in every channel physics permits, and that we are only beginning to learn all the languages in which it speaks. And we considered the Fermi paradox through the lens of the void and understood that the space between galaxies is not merely a distance. It is a permanent and nearly absolute barrier, enforced by physics itself, ensuring that each galaxy is its own cosmos, each island universe isolated from the others by timescales that exceed the lifetimes of stars. Now let that all settle. Let the journey rest. Because the last thing I want to say to you tonight is not about the emptiness. It is about what the emptiness means, not as a scientific fact, but as something closer to a gift, an unexpected one, a gift that the universe did not intend. Because the universe does not intend anything, but that emerges from its nature as surely as the cosmic web emerges from gravity and time. The voids exist because matter had somewhere better to be. That is the fundamental truth behind all the supervoids and the empty spaces and the intergalactic silence we have traversed tonight. The voids are not failures of creation. They are not the parts of the universe where something went wrong. They are the direct, necessary, inevitable consequence of the same processes that built everything that is beautiful and complex and alive. Gravity pulled matter together. Gas collapsed into clouds. Clouds collapsed into stars. Stars forged heavy elements in their cores and scattered them in their depths. Those elements assembled into planets. On at least one of those planets, chemistry became biology, and biology became mind, and mind became the capacity to look back at the void and understand what it is. The void had to be empty so that the filaments could be full. The darkness had to be deep so that the stars could be bright. The distances had to be enormous so that the islands of matter had enough space to collapse, to form, to become the complex, structured, improbable things that they are. A universe without voids would be a universe without galaxies. A universe without loneliness would be a universe without life. The emptiness is the price of everything that is not empty. And tonight, from your small warm place on a small warm planet, orbiting an ordinary star in the outer regions of a spiral galaxy on a minor filament of a cosmic web that spans 46 billion light-years in every direction. Tonight, you received a signal, not from another galaxy, not from across the void, though the void is everywhere around you. From here, from the accumulated human effort to understand where here is and what it means to be here. Imagine for a moment a single photon. It leaves a star in a distant galaxy, a galaxy perhaps 200 million light-years away, somewhere in the faint periphery of the cosmic web. The star does not know it has emitted this photon. There is no intention, no message, no purpose. The photon simply exists and travels, as photons do, at the only speed the universe permits. It crosses the intergalactic medium, that cold, thin, ancient plasma. It passes to the nothing of the void, unimpeded, unobserved, carrying its small quantum of energy across a distance that no human word was built to contain. It travels for 200 million years. It enters the Milky Way through the galaxy's diffuse outer halo. It passes between stars without hitting any of them. Space inside galaxies is also mostly empty, though a richer emptiness than the void. It finds its way, through some particular arrangement of the cosmos, into the inner solar system. It passes the outer planets, the asteroid belt, the orbit of Mars. It enters Earth's atmosphere and passes through it almost without interaction. It strikes a cone cell in the retina of a human eye on a quiet night, somewhere on the surface of a small blue planet that the universe spent 4.5 billion years making suitable for eyes, and for minds, and for the capacity to receive and understand what has arrived. The photon's journey ends. The information it carried, information about a star that may no longer exist, in a galaxy that has been evolving for the 200 million years since that light departed, becomes part of a conscious experience, becomes something seen and felt and perhaps wondered at. That is the gift, not the emptiness itself, not the silence of the void or the vast indifference of the distances, but the fact that across all of that emptiness, across all of that silence, something arrived. Something always arrives. The universe is separated by distances that dissolve every ordinary conception of nearness, and yet the light still comes. The gravitational waves still come. The cosmic rays still come. The universe speaks across its own void in every channel available, and here on this small, warm planet, we have built eyes and ears and instruments sensitive enough to hear it. We are not separated from the cosmos. We are part of it, made of it, assembled from the atoms that were forged in stars that lived and died before a sun was born, in galaxies that may no longer exist in the form they had when the light we see tonight departed them. We are, in the most literal chemical sense, the universe looking at itself, using the very matter that the void shaped into stars, and the stars shaped into heavy elements, and the heavy elements shaped into biology, and biology shaped into minds, to contemplate the void from which all of this arose. The space between things is vast, but we are here on the near side of all that distance, warm and awake and listening, and that, in a universe mostly made of cold and dark and silence, is a remarkable thing to be. Rest now. Let the void be what it is. Immense, quiet, ancient, beautiful. Let the filament of the cosmic web trace their slow architecture across scales your mind cannot hold, but your sense of wonder can touch. Let the supervoids be empty as they must be, as they have been for billions of years, as they will be for billions more. Let the dark matter do its invisible work. Let the dark energy carry the distant galaxies gently over the horizon into the unreachable beyond. And let yourself be, for this moment, exactly where you are, a small, improbable, luminous thing in the middle of the greatest darkness the universe has ever made. You are the space between things, learning to know itself,